היא דוברת אנגלית, אז היא לא כל כך הבינה את המושבים שלנו. ג'ניפר, יש לה מדיקל דוקטור בטקסס יוניברסיטי, היא עכשיו עושה פוסט-דוק בבן גוריון בקמיקל אנג'ינירינג. רוב העיסוק שלה זה ב-Laws of Pattern Development. היא תדבר באנגלית, והנושא ההרצאה, אנחנו תרגמנו לעברית, הוא אי סדר במסווה של סדר, מדע האקראיות.
Shalom. Really been interesting being here. I don't understand all of the talks, but at least with some of the pictures and a few of the words, I've noticed some of the talks are very nice. So what I'll be talking about is disorder disguised as order. And we're going to begin with an experiment. I'm going to show you a little movie, and then at the end of the movie, we're going to ask a question about disorder. So before I begin the movie, I want to tell you a little bit about the experiment. So in this experiment, we have steel pins, needles or rods. They're about this big. They're dumped randomly into containers. We can pick any size or shape of the container. But what I'll be showing you today is a circular container. This container is located on a shaker. So this is the top view, and now we're looking at things from the side. This is the container. This is the shaker here. We turn the shaker on. It bounces the container up and down. And then with the camera, we can take pictures is what's happening inside the container. Now there's a little bit of a thickness in the container, but we're still going to consider that this is a two-dimensional system rather than a three-dimensional system. Okay, so now the movie. So this is how it started. The shaker turned on. And the rods are behaving in some way. Okay, so now after hearing so many talks about disorder, so we can ask the question, which image has the most disorder? Is it the first image or the last image after all the shaking? So shall we take a vote on it? Who thinks that the first image has the most disorder? Okay, so a good number of people. And how many people think that the last image has the most disorder? A few brave souls. Very good. So the actual answer is the last image has the most disorder. Now, when I first learned about this, I thought that this was very surprising. And so what we're going to do is that we're going to start with ideas that are very familiar to us, and then we're going to build upon these ideas until we reach an understanding of something as complex as this. Okay, so we're going to start with dice. So this is something that we're very familiar with. The dice has 6 faces, and you can have any number from 1 to 6. And basically, we're very familiar with the idea that each face is equally likely, but we don't have to take this on faith. What we can do is that we can perform the experiment and we can measure this. So here on the bottom is the numbers that you can get for the dice face. We roll the dice once, and then we count what we get. And for this particular roll, we got the number 6. Okay, so we can do this several more times. So here we roll the dice 10 times, and we see this particular distribution of the dice. So basically, we got number 1, we had 3 times for the number 2, and so forth, and etc. Now we can spend a very long weekend and roll the dice 10,000 times. And what you see is that when you look at what number can come up, you find that it's more or less equal. And this is what is meant by equal probability. And what's interesting is that you see this particular disorder only after you've done the experiment many times over and over again. Okay, so now let's move on and think a bit geometrically, and we're going to start with just one rod. And here's our rod, and it exists in a particular space. We can pick any space that we want, and what we're going to do is we're going to choose a space that matches the experiment. So we want to figure out what's going on with our experiment. Okay, so there are two possible things that can be disordered with the rod in space. And what you have is that you can have a disorder in position. Basically, the midpoint of the rod can be located anywhere in the container. And we have disorder in orientation. Basically, the angle that this rod can take can be any angle. And we say that there's equal probability in these events. But again, we can do the experiment. And just like rolling the dice, so here is our experiment. We have a rod, and we ask the computer to randomly put the rod in any location here, and to randomly orient the rod in any location. And what we do, just like the dice, we make a record of what is happening. And just like the dice, we have many, many experiments. So this is an example record of what you could get if you had 5,000 events of putting the rod randomly. Okay, and just as a really fun aside, so if you go to the Contemporary Museum in Naples, Italy, what you find is that there's a particular exhibit called 10,000 Lines. And so artists do find lines in space interesting. So if you heard the talks from this morning, you know that because the humans, we were not very good at generating things randomly, but this was the artist's idea of 10,000 lines in a given space. So it's reminiscent of the picture we saw earlier. Okay, so let's go back and measure our disorder. So we're first going to start with disorder in position, and what we're interested in is where the midpoint of the rod can be. So here in red are colored where all the rod midpoints are. And you see that there's a little bit of a difference between the boundaries. So what happens with the boundary can be the topic of a whole other conversation, a whole other talk. So we're going to ignore the boundary for now, and we're just going to think about the rods in the middle. So how do we measure disorder in position? One way to do it is that you can just take a slice through the container, and then you can count how many times you find the rod midpoint in a given location. So that's what we did here. So 0 is basically the center of the container. The positive values here are off to this side of the container. The negative values here are off to this side, and we find that it's basically equal. You can find the midpoint of the rods in any location along this slice. Okay, so now we're going to do something similar with orientation. And here in this image, so basically this is a recording of many, many events. Again, we're going to ignore what happens along the boundary. Special things happen there, and we're going to focus what's going on in the middle. So the rods have a color, and basically the color depends on which way the rods are pointing. So in this example here, we have red showing that the rods are going up and down, while the cyan color, for example, shows rods that are pointing right and left. So you can see in this image that it's fairly disordered, but we can be more precise. We can measure the disorder. And this is what we've done here. So we've just arbitrarily chosen our angle 0 to be here. We could have picked anything, but we just choose it this way. Here's our angle 0. And rods that are pointing up like this have positive angles, and rods that are pointing down like this have negative angles. And what you see is that all the angles are equally probable. Okay, so now we have an understanding of what happens with one item. So now let's make the picture a little bit more complex, and we'll have more than one item. And we're going to go back to our picture with dice. So we know that each individual dice behaves randomly. We saw that at the beginning of the talk. But now what we're interested in is the sum of the dice faces. So what we're doing here is that we're creating an interaction between the two dice. And what you find is that the number that comes out of this summation is not equally distributed. So where does this come from? So for example, if you want to get the number 2, there's only one way to get number 2. The first dice has to come up as 1, and the second dice has to come up as 1. However, if you want to say get the number 7, there are many ways to do that. So the first dice can be a number 2, and the second dice could be 5, or it could be the opposite. The first dice could be 5, and the second dice could be 2, or 3 and 4, and so on and so forth. And so if you add more dice in the interaction, so say you sum 10 dice together, you find that the preference for certain numbers, so the summation increases. And you can continue this even further. If you add 100 dice, you find that the preference for certain numbers is even stronger. So what we mean when we say this order is maximized is basically saying that you're most likely to see that which is most probable. So in other words, there are many thousands of ways you could sum up 100 dice to get, say, the number 375, but there's only one way you can sum up 100 dice to get the number 100. Okay, so this is what we mean by this order is maximized. So now let's take this idea to many rods. So we know that one rod cannot exist in the same space as another rod. So now we have the idea of excluded space. So let's look at this a little bit closer. So suppose we have one rod and we fix it up and down. We could have fixed it any particular way, but we choose just up and down for our purposes of discussion, and we have 3 different examples here. And now let's suppose that the second rod has a particular orientation with respect to the first. So for example, this rod has a 90-degree angle between our first rod. This second rod here is parallel, or has 0 angle between this rod. And our second rod here has some arbitrary angle with our first rod. And this space here, this area that's shaded in blue, is basically the area that the midpoint of our second rod cannot go because the first rod is present. And what you see here is that this particular space, excluded space, depends on the orientation between the rods. So this is very interesting. So the angle is basically related to orientational disorder. And the amount of space here takes away from positional disorder. So if you have more space, you have more positional disorder. If you have less space, you have less positional disorder. So what's interesting to see is that if the rods align, if you lose orientational disorder, you see that the excluded space is the least. That means that there's more room for positional disorder. So now we have a link between positional disorder and orientational disorder, and you can't think of the two separately. They're together, they're coupled. So when would something like this become important? So we can think about it in this cartoon. So if the rods are not so many in number, and if they have a lot of space to be in, then you can have maximum disorder of orientation and maximum disorder of position. However, if there are many rods in a small space, you have a problem. How do you put many rods into a small space? It's very difficult if you have the angles pointing any which way, as we saw in the previous slide. So what happens is that you lose orientational disorder, but you gain a tremendous amount of disorder in position. Okay, so we can see this with the experiments. So we're going to start with low rod numbers. And basically here, each image is an event, and we ask the computer to put several rods. It looks fairly disordered, but we can actually measure this. We're going to focus only on orientation, since that's where the most action occurs. So again, we just chose our angle 0 to be along this direction. And just to remind you, the positive angles, the rods are pointing up, while the negative angles, the rods are pointing down. And you see that with this many number of rods, it's all the angles are equally probable. Now let's go and see what happens with a large number of rods. Okay, so when you have a large number of rods, say here, you have a bit of a problem as far as how you start these experiments. we do is that we begin them with our best guess of disorder. So we ask the computer to put down a rod at a time, and the rod can go anywhere and be pointed in any direction. And this is basically what the computer gave us. So this is our best guess of disorder. Now, we don't know if disorder is maximized here. If you remember the picture with 100 dice, you can get a very different picture of disorder if things are interacting. So this is a static picture, so what we need to do is we need to get the rods to interact with each other. And basically we ask the computer to move each rod randomly. So the computer moves each rod randomly by position and by orientation, and we let, in this way, the rods can interact with each other and they feel the space constraint. And this way they're able to find the most disorder. So I'm going to show you a movie. It starts with this configuration, and then the computer randomly moves the rods. And if you remember, it started with this, our best guess of disorder. We let the computer randomly move the rods, and this is what happened. So now we understand why this occurs. This is because the space is very limited. When space is limited, there's a competition between the disorder in angles and the disorder in position. And so what happens is that the disorder in orientation is sacrificed, and there's a tremendous gain in the disorder in position. Now what we see with our eyes is the loss of disorder in orientation. So that's very dramatic. Everything looks like it's pointing in the same direction. What we can't see with our eyes is the gain in the positional disorder. So now we can go back to our experiment. So we began with our best guess of what a random rod orientation would look like. We dumped these into the container. We turn the shaker on. The shaker jostles the rods. The rods can feel that there's not much space available, and this transition occurs. So the rods are all oriented in the same direction. And we can measure this loss of rod orientation. We can measure the loss of rod disorder and orientation. Basically, we look at what's happening in the center. This time, our angle 0 is going along the direction that most of the rods are pointing. And then we have the two sides from that. So you see that there's a strong peak for a particular orientation. Now, just a little quick demonstration that this doesn't, it's not limited to rods. You can create other situations where this is important. And just really briefly, so if you have, say, spheres of two different sizes, you can play the same game between the competition of two disorders. So you have the competition of the disorder in the big spheres, the positional disorder, versus the competition of the disorder in position of the small spheres. And if the small spheres have a large enough number, they can push the two spheres together. This, again, is the excluded space that they're gaining. And what you see here in the experiment is that this occurs in reality. And you can also get something similar with rods and spheres. You find that when there are many spheres, the rods get pushed together. So basically, in conclusion, disorder can sometimes fool the eye. It's because our eye is not good at picking up all kinds of disorders. So entropy is maximized here. The disorder is maximized, so you have a whole lot of positional disorder. And this occurs whenever random objects or random events are coupled together or can interact. So for example, here they interact because of space constraints. And that's, thank you.
Energy to the system. So then, for me, it looks like anti-disorder.
So it's like, okay, so for the configuration. So basically the energy is zero if the rods are not overlapping, and the energy is infinite if the rods overlap. So this is, I guess, energy-less. You can think of it as an energy-less system, and it's just like rolling the dice.
So once you have this orientation, this is less energy than the first, the initial position.
So the energy is the same, but you're just not likely to see the initial position because there are more ways that you can arrange the rods in this type of configuration. So just think of it as like rolling the 100 dice. So basically the rods are coupled, and when they're coupled, there's certain events that are more frequently observed than others. So for example, with 100 dice, you're more likely to get some number in the 300 range, and only one way of seeing, say, 100, the number 100. So that's similar to what we saw in the beginning. It was one particular configuration, but really most of the configurations are along these particular lines here.
But in real world, do you measure a disorder by the amount of energy that is put into it?
So you can do that in certain systems. Not in the experiments that I've done.
Like
So
at home, I know